Right, I'll do that. All right. Hi, everyone. Welcome. Today's lecture in climate data science, our presenter is Dr. Joe Ko. He is a postdoc here at Columbia University. He has a PhD in environmental engineering and a master's in computer science from the University of Southern California. And right now he's working on integrating observations, simulations, and machine learning to improve the representation of ice clouds and atmospheric models. So thank you, Joe. Whenever you're ready, you can get started.
Thank you. Okay, I've never presented like this, so this is gonna be weird, but might have to get used to this. But welcome everyone. A lot of new faces I've never seen, but welcome here. Kara said that the PhD students are getting younger every year. But yeah, today I'll be talking about ice clouds, the clouds you see in the sky that are really high in the atmosphere. And the reason for this, so the reason for this title was kind of have a hodgepodge of different projects. I'm like, what would fall under this umbrella? And maybe something that everyone can relate to, like generally in science and even in life, is like, how can you compress a lot of information into something that's useful? And we want to do that for these ice clouds. So this is a roadmap of the talk. So first, I'll give a brief background of why this is an important topic, and then talk about the microscale complexity, or in other words, complexity related to the particle level complexity of ice crystals, and then relate that to the macro scale complexity of, how do those micro scale complexities impact the state behavior of the cloud overall. And then finally, I'll wrap up. And maybe just as a big picture background, complex systems are everywhere around us. So just 3 examples, there's many more: biological systems, material science, and of course, what we study here at LEAP, the climate or Earth systems. And these systems occur at different temporal and spatial scales, and all of these scales kind of interact with each other. And they range so many different orders of magnitude, and that's what makes this very difficult to model this in a computationally tractable manner. So, reducing or compressing complexity is mandatory for understanding these systems. Well, I did not expect so many people here, so I'm getting a little overwhelmed. But so basically, yeah, maybe a simple definition of compression is identifying what information matters. So without getting into the nitty-gritty of it, of course, there's like lossy compression where you lose some information, or lossless compression where you retain all the information, but without getting into detail, this is what matters. And here's some real life examples. For example, this stock market, right? There's like every microsecond, things are fluctuating for all the stocks, but generally people want to know some important trends, like on the right, like this S&P 500 trend. Here for physical systems with turbulence, on the right is a mathematical representation, which is a distilled representation of that with the equations, right? And another example, right? Like you might have like, this is very funny. I am laughing really hard, before emojis and, acronyms like LOL were invented. But this is some example of compression in daily life, right? And why is this relevant for ice clouds? It's because, as I mentioned, there's a lot of complexity at the single particle scale. All these crystals come in various forms. They come in essentially what we call habit, but that's just a shape. And that also dictates its properties and how they evolve and how they interact with the larger Earth system. And the macro scale complexity is these clouds are varying spatially and temporally over time. So how do you capture that variability without the computational cost exploding? And this is just a very overwhelming diagram of how cloud processes are represented in like weather and climate models. So basically, there's all these different processes, like the liquid droplets and the ice crystals. They interact with each other, they grow, they shrink, whatever, drop out, interact with each other in different ways. But the challenge is, how do you do this? Um, you know, and this is kind of a roadmap of how this is done in cloud modeling and Earth system modeling. So you start with some physics that you might know, and then for the physics that you don't know, you need to fill in those gaps with observations. So you take observations in the lab, you take observations doing field studies or other observations. Some people even like create artificial clouds like in cloud chambers, like Kara can talk a lot about that. And then you use these information to create a simplified model of the different processes, like a statistical model, and that's what you call parameterization. And then you plug those parameterizations into this large model of the Earth that we call this coupled system model or like Earth system model. And so I'll just talk about three projects that kind of relate to these, like measurements and how we can use machine learning to improve our understanding of the ice crystals with measurements. And then more on the macro scale, how we can use a bunch of simulations to improve parameterizations by improving like how we can estimate these unknown parameters in the model. Yeah, and without further ado, so the first study is kind of, at first glance, you might think like, how does this fit into the compression framework? But I feel like a lot of machine learning, there is a information bottleneck. For example, in this example, we're trying to predict from this image certain properties you might be interested in, like the mass of this crystal, the surface area of this crystal, or like the number of certain features, like these spikes on these crystals. And then when you think about it, if this image is like 224 by 224, then you're really reducing the dimensionality of this through a neural network, for example, to something that's like 1 or 2 dimensions. So there's a bottleneck, and you're essentially compressing when you do the supervised learning. So the way we did this is just a really classic supervised regression and classification. And the challenge was really with coming up with the training data to make this happen. And the way we did this was create artificial crystals on the computer, because with real crystals, we have 2D images, but we don't know, like, for example, we can't measure the simultaneous mass or the surface area of these crystals. So what we do is based on these scanning electron microscopy images that were taken from real clouds, we could kind of constrain or have a sense of like how big these crystals are in different dimensions. And then we can create randomly in the computer a bunch of crystals. And then using these synthetically generated crystals, you can train a supervised model. And that's essentially what we did, just showing you a visual quality check. On the left is a projections from real CPI images of rosettes, and on the right is synthetic. So we can see pretty close. And we also compared the distributions of different characteristics of these images as well for validation. And this is the pipeline. So for each generated crystal, you'll take a random 2D projection. And then for that 2D projection, you beforehand can calculate the things that you want to predict. And then basically have a pair of the image with whatever you want to predict. And then you train these regression models to predict the continuous things that you want to predict, like mass or surface area, and classification models to predict, for example, things like that are discrete, like the number of arms on these crystals. And then you test on unseen data. So very classic, just supervised pipeline. And in very briefly, it works. So on the left is just a training showing a linear baseline with the linear regression for mass and surface area. And as you see that a lot of the biases on the lower ends are eliminated when using like a more complex ResNet, which is a convolutional neural network. And the correlation coefficient is a lot better as well. And just to show also for a classification task where we want to predict the number of arms on these crystals, we see that the ResNet or the convolutional neural net does a significant better job at predicting the number of arms compared to a linear baseline, which is a logistic regression. So the convolutions in this case, which are like these filters that look through the images, they drastically improved the performance for this specific task. And further details in the paper that we wrote up, but we also tested this with two views, because there's some instruments that can take 2 simultaneous views of the same crystals. So what happens when you add that? Do we get a performance boost? And short answer is yes. For all of the outputs that you want to predict, we see a performance boost when we add another additional view. And furthermore, we can quantify which angle is actually better. So we saw that this 90-degree angle or orthogonal view angle was actually better than this 120 view angle, which was surprising because this FIPS instrument is newer and it was actually designed at 120 degrees to get a better view. But then from our model, we actually saw that this orthogonal view or this from the older instrument, this 2DS instrument gave better performance, which is kind of interesting. And how does this tie into the whole climate modeling business? So basically, we want to use real observations to constrain the relationships that we use into the climate models, right? So that's where this fits into the whole picture. For example, we can encode the complexity or the shape of the ice crystals into a relationship, for example, between the mass or the size, or like the surface area and the size, and then that can be plugged into a parameterization or be used to like refine existing parameterization. So key point for this is we developed a supervised machine learning framework using synthetic crystals to predict some properties we might want to know from 2D images. And then second, so we're still sticking with the microscale complexity, but now what happens if we have no labels? We just have a lot of different ice crystal imagery. Is there something we can still learn about these crystals? And that's where self-supervised learning comes in. And this was a collaboration with some computer scientists. We adopted their model with our data. And basically, it goes like this. So we train a self-supervised pre-trained model, and then downstream we use these like condensed or compressed representations to do useful tasks with like fine-tuned smaller models. That's the big picture of it. And what we used was this IBOT VMF framework that was developed by our collaborators, and this falls in a distillation with no labels category of self-supervised learning training. And for the model G, which you see here on the screen, we use a small vision transformer. So this model is trained without any labels so that essentially the student network or the vision transformer matches the evolving teacher network over time, and is trained to minimize the loss of the probability distribution of these prototype like representations, which is signified here with this probability distribution P. But without, zooming out, what it learns is these clusters of representations on like a sphere, but in high dimension. So if you can imagine like a sphere is in 3 dimension, but a hypersphere is like in, like hundreds of dimensions, right? And it learns to, and the reason why we chose this is because our collaborators found that using this framework, it could separate the representations of images like in a more clean linear fashion, and I'll demonstrate that. So this is some details about our data. So we had 3 million unlabeled images of ice crystals, and then we had a smaller labeled data set that was like labeled by experts in terms of like what type of crystal they are, and that was 20,000. And then we also had some, well, this is kind of old. We have an updated data set, but we had a smaller 500K data set that also had corresponding environmental data, like the temperature and humidity that corresponds with that image. And then this final data set down here is a curated data set that was used for some other iterations of pre-training that help with the pre-training, because we did this pre-process of hierarchical clustering, which helped with the data imbalance. And data imbalance means that, for example, there might be a small amount of certain types of crystals, but a large amount of other types of crystals. And then this hierarchical clustering essentially helps balance that. And the way that we validate if our model is learning something useful is we take the embeddings from the vision transformer that was pre-trained, and then we train a simple classifier using those embeddings or those representations. In our case, we just use a KNN or logistic regression, so basically a linear baseline. And then if we see a robust performance on the classification with using these simple models, we know that the representations are robust and they're linearly separable. So we saw, and for our best models, we saw performance of up to like 84, about 84% accuracy for a logistic regression classification. And also just to test, so are these representations actually better than something that you can just like manually diagnose from the image, right? So for example, you can calculate certain characteristics of the crystals directly from the image, and can we use those to train like a logistic regression to classify instead? And to test this, we manually derived 13 different features directly from these images. For example, like the circularity of the image, the aspect ratio of these crystals. And then we used these manually derived features to predict the class. And then we found that the accuracy was about 57%, which shows that, yeah, the self-supervised learning model is learning more features that cannot be just manually extracted like through a human. So that was just a simple validation there. And this is just to illustrate something that I just wanted to show, because my gut instinct is to always like try to visualize things in 2D. So these embeddings are like 384 dimensions. So my instinct is to reduce this to like 2D and just see like, do the clusters actually separate like how you'd expect in like visual space? But it actually doesn't. Like usually with UMAP and TSNE, which are like non-linear dimensionality reduction techniques, they do a pretty good job at separating clusters. But the weird thing is that we're using these embeddings that lie on the hypersphere. And this kind of proves the point, right? That by lying on that VMF hypersphere, things are like better linearly separable, but when you try to non-linearly separate them, like essentially things get strange. And you see that here visually. And I just also validated this with taking cross sections of the pairwise PCA components, and you can see like in different cross sections, different clusters kind of emerging. And to know for sure, okay, I know, yeah, I know this is kind of an aside, but I thought this was kind of interesting, so I'm gonna dig into it. To know for sure, I wanted to see like how can I visualize this? So basically, I used the logistic regression weights that were learned with that supervised training. And then I took the projection of each sample, so like the dot product between the weights and each sample, and then did that pairwise between each pair of classes. And then you can think of that dotted line being like the linear hyperplane that separates all the classes within the logistic regression. And we can see in this way, things are being separated, we just can't see it. And I just thought that was like a pretty interesting, it was kind of like a rabbit hole, but like I thought this was cool. So now to back up, we like learn these lower dimensional embeddings of the images, 384 dimensions, like what can we actually do that's useful for science? And one thing we can do is like quantify the diversity of crystals in real life clouds, which has not been well constrained before. And we can also do this as a function of some key environmental variables or other variables like crystal size. So what I'm demonstrating here is just as a simple example is how does the diversity, so this kappa metric is like a metric of like concentration within the latent space. So low kappa means high diversity and vice versa. So it's just showing the trend of crystal diversity as a function of temperature and also as a function of the different campaigns, which are indicative of like different cloud systems, right? So we see variability within the different cloud systems and also variability as a function of temperature, and then same with particle width as well. But for particle size, this kind of is counterintuitive because I would have, or maybe some other people and I would have thought like particle width, larger particle widths would indicate more complexity, but we're actually seeing the opposite based on this representation that we've learned. So this is something that would have been kind of difficult to do without some kind of condensed representation because the images are so high dimensional. And another thing we can do is like compare the similarities between different types of crystals the essentially using some similarity metric between the centroids of the clusters that we've learned. So this is a matrix showing the cosine similarity between different classes. So that the diagonal is showing like how diverse is the class within that crystal type. So a higher number indicates that there's higher diversity within that class. And then the pairwise off diagonal values show like how similar are the two different types of crystals to each other. So now we can, based on some kind of objective metric that doesn't depend on like expert knowledge, we can start to draw these relationships between like the representations in terms of like its shape at like a larger scale. So this is something interesting that we can do with these compressed representations. Another thing is we can start to think of a probabilistic habit diagram. And what a habit diagram is basically showing you like for a given environmental condition, for example, on the left is like ice supersaturation and temperature, and ice supersaturation is just like humidity. So for a given humidity and temperature condition, like what kind of crystal would emerge at that condition? And on the left, this was from lab measurements actually, where like the supersaturation and temperature were kept at a constant rate. But we know that in the real environment, things fluctuate a lot, and crystals see a lot of different as they travel through the atmosphere, a lot of variation in their environmental conditions. So what we want to do is create something that's probabilistic using the actual crystal imagery data that was taken from the plane. And then we started doing that basically. And this is just showing a subsample of 10,000 images. And we basically reduced the 384 dimensions down to 3 dimensions. And then we mapped those 3 dimensions to RGB space. And then we colored that using the RGB. And we can see some clear separation in the temperature, which means there's a strong correlation to temperature, but then not so much with supersaturation. And this is kind of maybe expected because there's like really high fluctuations in supersaturation. Like when you measure supersaturation at 1 second is gonna be completely different in another second. But the temperature actually would be less fluctuating because it's more a function of kind of its height. So this is kind of confirming what we know about like real world conditions and how they relate to like ice crystal diversity and habit. And we want to expand on this work. And that just leads to this work we're doing to create this unified data set of the images themselves, the image embeddings, and also associated auxiliary data sets, such as like the environmental conditions and other crystal attributes. So far, we have about 3 million records from across 11 field campaigns. And this was a very laborious effort because if anyone's worked with in situ data, like, you know, the data is not like very uniform, and every field campaign has like different types of formatting and like different metadata. So I had to go through each of these campaigns and like essentially parse out the data and then put them in a unified form. But our goal is to make this open source so that other people can kind of explore this and also make this evolving. So add other data as well as in addition to these 11 that we've added so far. And this is also a manuscript that we're preparing for a data manuscript. So the key point of 2 is that we can use self-supervised learning methods to learn some distilled representations of ice crystal morphology, and then this can be useful for some novel downstream science tasks. And shifting gear now is now going to macro scale. Oh, let's just say macro scale. When micro scale is now to the macro scale. So now if we simulate these clouds like on a computer and we perturb some inputs and then see what happens to the outputs, like what can we do in terms of understanding the sensitivity of the model itself to like certain parameters of the cloud microphysics or certain structures of the cloud microphysics, and can we constrain the uncertainties due to these parametric or structural differences? And also, can we like estimate parameters based on observations, and how do we best do that? So I'll discuss a little bit about that, shifting gears. So just giving an overview of how microphysics schemes work in a climate model. So you'd have X, which is the state of the essentially the population of ice crystals at time t. And then the microphysics schemes does a bunch of calculations for all the different processes that will change these ice crystals. And then on the output, you'll get xt plus 1, which is a distribution of the ice crystals at the next time step. This is just very simplified kind of mental model of how microphysics works. And two things that affect this are the structural uncertainty, which is like, you can imagine there's different equations that are governing how the crystals grow and shrink. But there's lots of variance of these equations, and that is what I'm referring to as structural uncertainty. And then within these equations themselves, there's parameters or like empirical or semi-empirical parameters that may be partially known or completely unknown. And these contribute to what is known as parametric uncertainty. And we want to figure out a way to understand these uncertainties or like reduce them. So what we did was, oh, okay. Forgot to include the slide. Well, basically what we did was we ran a simplified climate model, which is called a single column model. So it's basically, instead of a full 3D model, it's just a 1D model. And we ran 500 different ensemble members. And for each of these members, we varied the structure, and then we also varied randomly the parameters within these single column models. So one structure that so two structures that we analyzed. One was with this unified ice scheme off. And what that means is, like in a classic climate model, there's this thing called ice snow auto conversion. So there's this free parameter called DCS. So once an ice crystal becomes the size of DCS, it becomes snow, and the properties of that ice completely change. So you can imagine this is like very unphysical, but that's just how it's been modeled up to now. And that's a newer scheme where it eliminates this DCS parameter, and there's a single category of ice eliminating this unphysical abrupt shift. And then for parametric uncertainty, we just chose like 5 different parameters that we thought were important. And the top 3 represent ice complexity. So this actually relates to what I talked about in the first part of the talk with like the microscale complexity. This is the way that the microscale complexity is represented within like the macroscale model. Oh yeah, so this, I guess this is the overview of what I was talking about. So once we run a bunch of these simulations with different input parameters, then you could train like an emulator or like a neural network to basically map the parameters to the output state of the model. For example, like how much ice there is coming out of the model, etc. And then once we have that fast emulator, we can do these other things that we're interested in, like uncertainty quantification and parameter estimation, which I will talk about next. So just as a case study, Spartacus, we use Spartacus campaign as a case study. So this was a 1D model run over like the Oklahoma, the middle of the US, for a 1-month period in 2010 April. And so on the left, what we're seeing here is kind of this difference due to the structure. As I mentioned, like having that unified ice scheme on versus off. So in the blue is with the unified ice off, and red is with unified ice on. And we see due to the difference between these two distributions is showing like the effect of having these different structure. And for example, with precipitation, we see like a really huge difference. With the total ice water path, we see a really huge difference. And this is total precipitation, including like convective. I did check that. And then this is for parametric uncertainty. We can run some sensitivity analysis, basically to see like for a perturbation of the input parameters, how much does that affect the variance of the output? So this is like a variance decomposition method essentially. And that also relies on the emulator that we had trained in the previous step. And and furthermore, you can also decompose the effects to like the direct effects. So what's the direct effect of a single parameter? But you can also isolate indirect or interaction effects as well using this type of method. And you can see like the usefulness of this is to know like how sensitive the model is to like certain parameters. But so this is the quantifying uncertainty part, but we want to go further than that. So say like we have some observations. How can we best estimate the parameters and then estimate the uncertainties given some observations? And so the first three steps is what I already talked about. And the last step is what we call parameter estimation using some type of like Bayesian inference, for example. And then the challenge with this is choosing what statistic you should optimize for. So you can imagine you have model output, and then you want to compare that to like an apples to apples comparison of observations. But do we just compare the means? Like, do we compare like some slices? Do we include the standard deviation? Like, what should the metric Z be that we're minimizing or basically optimizing for? And I wanted to explore that using latent compression. And this is kind of the big picture workflow. So the stage one is learn some representation of the data Y, and Y is like the output from these climate simulations. And this can be any number of techniques you can use. You can use like dimensionality reduction, some decomposition like wavelets, or like compression with like nonlinear methods like variational autoencoders. And then you use that Z, and then we can match, and then we can similarly encode observations using that same model, and then optimize in that latent space using what we call Markov chain Monte Carlo, which is essentially like a random walker that walks within this parameter space and then converges to the optimal posterior given some observations. So I tried with two methods just for demonstration. First is like a linear baseline with PCA or principal component analysis. And then we just use like the first n principal components and we say like this is some linear latent compression. Another method is to use something more sophisticated like a variational autoencoder. And what you can think of an autoencoder as like two neural networks. One is an encoder that's like compressing the data, and the decoder is decompressing the data, and then it's trained on a reconstruction loss that basically says like, oh, we want the reconstruction to be as close to the original data as possible. And we do the same workflow. And some more details about this. So we use a dimensionality of 32. And then we used also 6 different output variables. Sorry, it's a little small, so you can't really see them. But output variables that are related to cloud microphysics. And these are like 1D time series on the bottom. Here are like 2D time series where the x-axis is time and then it's vertically resolved. And for the PCA, what we did was basically like concatenate all of this data into like a gigantic vector and then compress that to 32. So it was like surprisingly, I'll show you, it surprisingly kind of worked. It's very surprising. But so these are the posterior results. So basically after running the Markov chain Monte Carlo, oh, I forgot to mention this is a known truth test. So we're using one of the modeling ensemble members as a ground truth because we know everything about that member, and I chose one that's like directly in the middle of the parameter space. And then on the left is using a crude statistic, which is just the brute force like mean over everything. So there's no spatial or temporal kind of information captured in that mean. And you can see the posterior is kind of like all over the place. The distributions look very strange. And then on the right is PCA, and then using the VAE, 32 dimensional each. And then progressively, we see like the posterior distribution looking more normal and also greater alignment between the median of the posterior distribution with the ground truth, which is in blue. Or I forgot to mention, yeah, the ground truth is the blue. And then the red is the median, solid. And then these are the 95% credible intervals. So it's just like a Bayesian way of saying like the parameter will fall within this range, 90%, 90 by probability of 95%. So we can see visually that the constraints are getting better and also the estimate is also getting better itself too. And just to zoom in a little better, so you can kind of see, I just got rid of the PCA one, but you can really see the improvement of the performance here. And I think this is promising direction to move into, but next I will say like the challenge is observations. Because I mean, it's great like within this ideal framework to test these methods, but using like real observations is really hard. Like for example, here is what I showed earlier, right? And the black line is the observation for that same like field campaign. So this is showing the total ice water path is conveniently sitting within the two distributions. And then this is the total cloud cover. So basically it's showing like there's more cloud, but then also less rain. So that's obviously some structural deficiency within the model. And maybe not all attributable to ice, because that's only one type of parameterization within the model. And just some additional wanted to show you some what these observations actually look like. So on the left is the radar reflectivity, on the top is the ground truth from like real world observations, and this is what is came out of the model through like a forward radar simulator. And then here is the precipitation rate. The top is the ground truth, where we see larger spikes of like intense precipitation, but for very shorter periods of time, whereas the model will have longer precipitation events, but like shorter or like smaller magnitude. And then on the right is ice water content, which showing like essentially like how much ice is there at different heights. And the top, this is observations. And another challenge is like missing data, right? Like how do you deal with this when there's missing, if you're trying to, for example, do that latent state estimation framework and you have missing data, how do we deal with that? So you have to correct for this or account for this in the training. So yeah, some challenges, a lot of challenges we have to work with moving forward and thinking about how to actually do this. But the key point for this was that we can simulate lots of climate realities, essentially by perturbing some unknown parameters and seeing what happens to the output. And then we can, with the help of machine learning and like compression, essentially with these latent metrics, we can help improve, hopefully, the parameter estimation process. So yeah, in conclusion, these are the 3 projects we talked about. We'll just, yeah, I won't go through them. But yeah, in conclusion, is less more than is more. Yeah, this is just showing my age because I feel like these are popular when I was in college. But yeah. And thanks to all the collaborators and yeah, I will just leave it here.
Sorry, I'm just getting closer to the mic. We have plenty of time for questions, either in the room or if you are on Zoom, you can feel free to just unmute yourself and ask. And are we hoping that the audio comes out here?
I hope so.
Your audio's on. Your speaker's on? Yeah.
Should we start with the early career scientists?
Yes. Do our early career scientists have questions? Ian, you got really excited about something. No?
I don't even remember.
Okay. Both of you were like pointing at the screen. Okay. Anyway, yes, we can open up for questions.
Yeah. Yeah.
So you had your the VA, the different the PCA, the VA, different ways of compressing the data. And then the result is sort of MCMC, right? And you're like, okay, what's the best thing that I can get there? Maybe it's like I get the true value close to the mode of my distribution and things like Gaussian. And it's like, okay, yeah, I've done a good job. So I guess that's a criterion that you can set, right? And you could be like, that's good. Like, this is better. Did you then use that is that used in like the derivation of the VAE, or is that something that could be like piped into that pipeline somehow, so that like that is somehow it's choosing the latent basis that is best for the parameter inference?
Yeah, I see what you're saying. So more like kind of like an online type training
Yeah.
situation. Yeah, I thought about it, but it's just much easier to do it
Yeah.
separate. Yeah, something to explore, definitely. I don't know.
I have a question. So I'm curious, your current latent matrix is defined like a Euclidean distance, right? I'm curious if you have tried other metrics like cosine distance, because that's the one I'm using. Basically, it's asking. I'm asking, do you think the distance in the latent space or the angle difference in the latent space, which one makes more sense? Because my findings are the cosine distance makes more sense for either parametric uncertainty or um, calibration. Yeah.
Yeah, that's something I need to explore more. But that's a good point. Because like, I mean, I guess goes back to the point of like in latent space, things can get weird with distance, as I'm sure you know. But yeah, that's something to like test with different types of metrics.
Cool. Thank you.
Oh, yeah.
I'm just curious, if you run your posterior samples like back through scan and just visually look at them,
Yeah.
do you see like, can you tell like the difference between PCA and the latent space, and does it look good in physical units, I guess?
Yeah, I need to try that.
Okay.
That's a good next thing to try.
Great talk, Joe. So that result where you said, I believe, correct me if I'm wrong, as width increases, diversity of the crystals goes down. Can that be boiled down to some sort of like very understandable sort of like structure on the crystals where they all, like you don't see a big one that just looks like some sort of like a column, right? It always has
Yeah.
arms. So is it because they all have arms when they're bigger and that adds some similarity to the structures?
That's possible. Yeah. But I guess one thing to also look at is the uncertainty range of that.
A fixed resolution.
Yeah.
So it's like you might be losing more details when you get the larger crystals.
Yeah.
It's like all the images are the same size effectively to make the machine learning model work.
Yeah. But I was kind of surprised because like aggregates are like pretty different looking and
Right.
but yeah, I don't know, something to explore more for sure. Yeah.
Well, another question. So about the observation, that was interesting. So the single column model is exactly that, like some sort of finite box size. I don't know what you're running it at, maybe a degree or something. So the observations, are those like looking up, are those from flight? How are those?
Oh,
How are the observations
yeah,
defined?
those are from vertically pointing radars,
So the
ground based.
field
Yeah, the
site
arm
no
field site.
Yeah.
Yeah.
So it would be hard then, I guess, to, take that whole SCM box and say, oh, the point measurement is kind of like representative. Have you ever tried to sort of say, okay, let's adopt an approach where you build in subcolumns, different subcolumn generators, and take the SCM mean fields and make fake clouds that are consistent with the SCM, and then draw from them randomly, or draw one that might look like, or a selection that might look like the point measurements, as a way to sort of bridge that scale back.
Yeah. No, I have not tried that, but that's a good idea.
These are SEM, they weren't LES.
Yeah, they're SEM. Yeah. Although, yeah, we did also run LES, but wasn't shown here.
Something very interesting, Joe. I forgot to say that. For this first project, have you looked at all? I think from what I understand, what you were doing was deterministic. If you make probabilistic predictions, like, do you see that can you be pretty deterministic, or do you think it'd be better represented by some kind of probability?
I guess since we're looking at like really large sample sizes, I'm counting on that to kind of give you the probability. But yeah, I guess there's nothing preventing you from like using in like a generative model or something. Yeah.
Oh, I guess my question is like, so say you have, I think maybe mass and you want to predict density or effective density. Can you do that from like, is the error doing that deterministically, like because you just don't have enough information? Or I guess you were able to get pretty good.
Are you predicting the output of the like deterministically? Is that what you're asking?
Yeah.
Yeah, it's completely deterministic. Yeah. But at least the neural networks that we use,
Yeah, okay.
yeah.
I guess I'm asking like, do you think that like would you try a probabilistic approach, or you feel like you have enough information to actually predict that very well?
I think it does pretty well. Well enough maybe for like the purposes of like improving the like for example the mass dimension relationship or something, because that already is like such a I don't know, like simplification of all the crystal diversity anyways. So yeah,
Yeah,
I'm not sure.
you have to cram it into the math dimension relationship, but maybe you could make that stochastic.
Yeah, that's what I'm asking. Should that be a probability or?
Yeah, I think so, probably.
Hey Joe, can I ask a quick question?
Yeah.
So I was wondering, so you use a lot of the dimension reduction method. So I would always wonder, like, do you think is there a way, in addition to the scores, can we check the negative effect of kind of losing the dimensions that you like the loss of information? Like, for example, it's just 5% of information lost because everything is nonlinear. Do you think it's possible that it lead to some unexpected like disruption? It's very open, but I just wonder if you thought about it.
Oh yeah. I guess that's yeah, I did think about that. And it's a little bit of kind of like just experimentation, to be honest, because like for example, the hyperparameter of like the latent space size, that's completely just like almost determined by you. I mean, you can do like some tuning of that, but I would expect, yeah, you to lose some performance if you lose information, right? Just I guess intuitively. And then with the PCA, like you can completely test this, like just use more or less components. And I just use 32 just to like match the VAE components, but that's just for illustration. Yeah.
You could also
Thanks. Because I was
learn on the parameters.
Just so you could mention learning the parameters.
You just quantify that information also.
Oh yeah.
Each latent representation, how much do you actually learn about the parameters from
Right.
yeah. Cool. Thanks.
So you had these two structures. Did you try estimating the parameters using the different structure for these methods? Like your output comes from the other set of, or the other structure, but you.
No, I did not do that. Yeah, I didn't get to that.
Well, I'm just curious, like, I mean, to have these, I mean, it's like a less extreme version of the structural differences between the observations and then. I'm just wondering if
Yeah, no, I haven't tried that. No.
The other thing is like with Greg's work, like in some cases it seemed like parameter perturbation could push things outside of the training ensemble. So did you do parameter estimations of the real obs? Like just see how far you could push the actual model, because I know some of those things don't overlap at all.
Yeah.
So it might be hard to deal with. But
Yeah.
I wonder how close you could actually like hammer the model. Not that you necessarily want to. There might be other reasons why you have a mismatch there.
Yeah. Yeah, I did not attempt with obs.
Yeah, I'm curious.
Just train the VAE on the real observations though, but like over more times
Yeah.
or something.
Yeah.
Than like that 1 month.
Yeah, I was also thinking like, is there a way you can, instead of training like the whole period, like do like day slices or something?
Yeah.
And then I don't know, there's just like lots of ways you can kind of cut and dice this. So it's really hard to pinpoint a optimal way to do it.
Have like a shared latent space with
Yeah.
real and the model.
If there are no other questions, then thank you, Joe, for thank you to everyone online for joining us. See you next week.
Bye.